Recording is rolling. It is Tuesday, March 17th. Today we're doing refraction and stealth law, which tells how light refracts mathematically. You guys remember yesterday we did ray diagrams for reflection, like for mirrors? And so today we're doing something similar, except it's going to be for, well, like these prisms here, or I got all the ones queued up. Tomorrow, you guys get to do Snell's Ball Lab. So I have all these fun materials up here with me today. Got a little laser light going. Okay. And tomorrow I'm gonna hand each of you guys a laser. You guys are gonna get in teams and do a lab version of this. Okay. You know what? I think I got the paper printed right here. It's double sided. One side looks like this, other side looks like this. Okay, so that'll be tomorrow's adventure. Okay. And then project Thursday, Friday, and that'll take us to spring break. And yeah, there we go. Okay, so what's this refraction? Give me guys. Oh, nope. Hold on. Uh, hang on, my computer is being all wacky right now. Okay, here we go. All right. They were say stick a straw, a glass of water, looks all bent. It isn't really, it's just an illusion, but this is light bending different ways, right? So why does it look like that? Now, the explanation here goes, okay, I have a lot of good demos, but I'm going to try to condense this in one class period here. Okay, that the speed of light is, well, 3 × 10⁸ meters per second, but really that's only true through a vacuum. When it goes through air, it slows down a tiny, tiny, tiny bit. But when it goes through a different medium like water or glass or whatever kind of plastic this is, then it'll slow down significantly more. And what happens when it slows down? Oh, do you guys remember this wave formula? I think we only covered this like a day or two. Right? So speed is equal to wavelength times frequency. You guys remember that? Right? So here comes this laser light. You guys see this red laser light? Right?
Okay.
Now, if you think about it being like a wave, though, really, you guys remember that light is a transverse wave? We were showing that with the polarizing filters. Right? Well, what happens when it goes from this medium to this medium? Say from the air to the water is a classic line. Right? Well, it's got to slow down. And as it slows down, then what else changes? Right? Well, if you look at all these wave fronts, could these be like the crest of the waves? Right? All these wave fronts, you guys see they're perpendicular to this red laser light. Right? Well, the frequency of those leaving the air, like here, boink, 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 right? You guys see periodically all these points where it leaves the air. Isn't that the same as it entering the water? Right. So, okay, so this frequency has to be the same on both the side of the air and the water. Right? But if it slows down, then something else has to change, which is that the wavelength has to decrease. You can see that here too. Here's the wavelength on the side of the air and on the side of the water. You guys see how it's shorter like that? Shorter? Well, if the wavelength decreases, then the resulting effect is that the light has to bend. Right? Now, everything I just walked you through is one perspective, like one explanation of this. Right? There's other explanations for what causes refraction. There's like weirdly enough, a whole explanation goes through quantum mechanics for probabilities and like uh, what do they call it? Another term I'm forgetting right now. Okay, but okay, how much could this light bend? How much could it refract? Now, do you guys remember yesterday when we were looking at the law of reflection? And I had a Paul Hewitt video playing. We were comparing the angle of incidence to the angle of reflection, but the angles we were measuring were with respect to a normal line to the mirror surface. Do you guys remember that? Okay. Now here I have this dash line is perpendicular to the plane where the medium changes, say from air to water. Okay. So uh, if you compare those angles, right? Look at this angle here, this angle here. Again, notice those are relative to this perpendicular line. Right? Here's the medium exchange right here from air to water. Right? Perpendicular to that, I'm measuring these angles theta 1, theta 2. Right? I can come up with this expression here, which is called Snell's law. It will tell you exactly what the angle change is going to be. Right? But what is this n right here? This n is called the index of refraction. And if you know how to read this, then you'll understand what this is. Okay? So guys, what is c usually in physics? The speed of light, speed of light in a vacuum, speed of light in a vacuum. So 3 × 10⁸ meters per second. That's a universal constant, right? What do you think? What do you suppose v is in this context? The speed of light through water, right? Which is slower. Right? I didn't say it would slow down, right? Did I say that light's going to slow down as it goes through like some plastic or some glass or some water? Right? Where's right. You guys remember that? Right. So the speeds are different. Guys, which number is greater? Speed of light through a vacuum or speed of light through water?
Refraction.
Yeah, through a vacuum. It's got to be faster. Yeah.
Does that mean steel light's faster in space than it is on Earth?
It is, yeah, a tiny, tiny bit. Yeah. So like the light from me to you is actually a tiny, tiny, tiny bit less than 3 times 10 to the 8 meters per second. Okay. And then through space, it's well, as fast as it's ever going to be, right? Something like that. Now, but the difference between the vacuum of space and air for the speed of light is so small. It's less than 1% difference. So, it's negligibly different. So normally you can just ignore that and just say the speed of light through air is just the speed of light in general. It's close enough for all these calculations. What you guys gonna do in your lab tomorrow? Okay. Uh, here. Let me show you guys some demos. Let's do some video demos here. All right. So guys, get a good look at this. Get a good look up here because I got so much class time. So I'm gonna try to make best use of my time here. Now, I do have some semicircular prisms like that, which are really nice, but also have some triangular prisms. I'm going to put something in your hands tomorrow, you and your teammates, but I got so many materials, so you might get this shape, you might get a different shape. Okay. But look how he's aiming the light. Now, I'll call that a laser light, whether it is or not. Okay. Notice that light beam. Notice how he's aiming it straight towards the center of what would be the circle if that was a circle. Okay. Now, that's an important point because there's some refraction that happens here. It's really subtle right now because it's nearly perpendicular to the plane here. Right? Oh, look, he has this line labeled normal line. Look at that, normal. Okay. Right. But that refraction, like whenever that light refracts out the other side, because this is a circular shape, this curve right here, the light will necessarily be going perpendicular to the surface, so it doesn't actually bend across this other surface, but it does bend once. It bends right here. So you're going from the air to the glass and the glass back to the air. You guys see that? Right. Guys, everybody following this? Right. And as it makes this angle bigger, 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 now you can see the effect opening up. Guys, which angle is bigger? This angle down here on the side of the air, or this angle here on the side of the glass? Which is bigger? Air. Do you think you could apply Snell's law to determine what is the index of refraction of this material? Actually, let's go ahead and do that. Let me pause it right about here. So, guys, what is this angle of incidence right here on the side of the air? Is that 45 degrees, I think? Is that 45? I think it's 10, 20, 30, 45. Let's call it 45, right? And then what's the angle of refraction here on the side of the glass? That's yeah, maybe a little shy of 30, maybe somewhere there, between 25 and 30. Okay. So yeah, let's go do a calculation, which is going to help you guys out tomorrow because tomorrow on your lab you're going to have to do a similar calculation. Okay. So I want to know what is the index of refraction of that glass, right? Of that glass going on. Okay. So I can set up n1 sine theta 1 equals n2 sine theta 2. Okay. Well, on one side I'll call it the side of the air, and the other side I'll call it glass. Okay. Okay. And we want to know what's the index of refraction of glass. Now for air, well, guys, if air in a vacuum is pretty much the same speed, what is C divided by C? What is that equal to? 1? Okay, so tomorrow when you guys do the lab, in place of n1, can you just put 1.0? Okay, so the 1.0, I think it's like 1.008, I think, something like that. We'll just call it 1.0. Okay, sine. And on the side of the air, we were looking at a 45-degree angle. Is that true? Okay, and then on the side of the glass, we were looking at, I'll call it 28 degrees maybe. I don't know, it's just eyeball on it, but pretty close to that. Okay. Do you guys know how to solve for n2? I think it's very simply divide over. So it is sine 45 over sine 28. I'm looking at n2 is 1.51. So it's probably 1.50. That's probably what it really was. Like there's probably some manufacturer that manufactured that glass to have an index of refraction 1.5. Okay. Guys, can you have an index of refraction that's less than 1? This is more than 1.5. Can you have it less than 1?
No.
I would say reasonably no, because if this number was like 0.9 or something, what that means is that the speed of light actually somehow went faster inside the glass. Right? The speed of light can never go faster than it can in a vacuum. That's just a universal constant. So it is a refraction you'll see is always more than 1. It could be 1.2, 1.3, 1.5 you're looking at like that. Now, guys, if you continue this story, guys, which angle is growing faster again? The air or the glass angle? Air. But wait a minute. If I zoom to the end of this video, or closer to the end, guys, this angle from the normal is approaching 90 degrees, isn't it? And this angle is kind of, well, it's not going to get there in time. If you guys see some reflection opening up, I didn't see that reflection before. That reflection is getting stronger, isn't it? And that refraction is getting weaker, right? In fact, if I go all the way to like 85 degrees, or I think that's where the video ends. Guys, this 85 degrees, that's as far as we can take this. You see some really weak refraction. You just barely see it. It's about 40 something degrees right there. You see something about 40 something degrees? Huh, right? That angle has a name. It's called the critical angle. So if I go back over here, actually, let's solve for the critical angle. Let's take this as a known value. Let's say we're allowed to know that now. Okay. Index of refraction of glass. Okay. And let's solve for critical angle. So I'm going to take index of refraction of air times sine of. I'll take this to 90 degrees. I know you were looking at 85, but it's pretty close to 90. So that would be like as far as you can go on the side of the air. Okay. I'll put a 1.5. Well, let's call it 1.5. Okay. Now let's find out what is the critical angle. Critical angle for that glass you guys were just looking at. You guys think we can solve that? Right. Let's try it. And tomorrow in your lab, you're going to do the same thing. Right. So get a good look at this. Take it. What is sine of 90 degrees?
1.
1. So 1 over 1.5. 1 over 1.5. Now let's equal the sine of the critical angle. So how do I find the critical angle? I have to apply what? Inverse sine. Yeah, inverse sine. You guys remember that? Okay. Inverse sine. We haven't done that in a long time. So equals theta critical. Let me see. So I can get hit second sine 1 over 1.5. I'm looking at, oh, hey, look at that. 41.8 degrees. Is that pretty much 42 degrees? Isn't that exactly what it looked like on the video? It's about a 42-degree angle, wasn't it? Yeah, yeah. Right. Right. And to give you guys another perspective on critical angle, could you have instead, notice he's shining the light in on the flat side, it's going refracting out the curved side, right? But could you do that backwards? Could you shine the light in the curved side and it refracts out the flat side, right? And the advantage of doing this is that, oh look, now which angle is growing faster? The glass side or the air side? Well, it's still the air side, but now it's the other side, right? And now, guys, how far can you go with this laser light before it won't refract anymore? 42 degrees, maybe about there, a little over 40 degrees. Here's 40, and then, look at that. He can go 40 and then like a couple more degrees, and that's it. Now this is hitting 90 up here, isn't it? Right? And everything else, guys, anything else he goes beyond that, is there any more refraction? No. It's all reflection, isn't it? It's all reflection. There's a name for that. It's called total internal reflection. Total internal. I think I got some posters for this. All right, so we talked about Snell's law. We got Snell's law. You guys got on Snell's law? Okay, get to apply that tomorrow. Okay. Here we go. So here's a fisherman and a fish. Okay, and this fish is sending out light in all different directions. Okay, but notice that any light that heads straight towards the fisherman actually gets reflected. It doesn't actually refract anywhere. Okay. Now the fisherman can see the fish, but in a weird place. Is what if there was a ray of light that goes up here and then refracts out just a few degrees and goes into his eyes? The fisherman perceives the light is coming from this direction and thinks the fish is just below the water over here. Says, aha! So he casts his fishing pole over here and say, why is it not getting the fish? This fisherman thinks the fish is just beneath the surface of the water, even though it isn't. It's actually way down deep here. Right? You guys notice that too. You guys ever notice if your friends are walking around in a pool of water, shallow pool of water, their legs look really short? It's like, hey, why are your feet so close to the surface? What happened to your legs? But it's just refraction, isn't it? Like that. Okay. So now we're on to ray diagrams. You guys ready to make some ray diagrams? Do some ray diagrams with the guys. And so put your name on your paper. How do you guys turn this in? Just like yesterday. Okay. Everybody got their name on their paper? Your paper? Okay. And this is ray diagrams. And I'm going to do dash refraction. Refraction. Okay. Yesterday we did reflection. Today we're going to do refraction. All right, so on the front side, we're going to do 3 ray diagrams. So get a ground line halfway, ground line about a quarter of the way up, and the ground line about a quarter of the way down. Okay, we're going to do 3 examples. All right, you guys ready for 3 examples here? Okay, and the length we're going to be using is, for all 3 of these, is going to be this shape length right here. You guys see this right here? Okay. All right, so let's go ahead and draw that shape lens. This is called a converging lens. So on the front side of the paper, these are all going to be converging lenses. So converging lens. Okay? You guys got converging lens? Actually, what would you call this object if you bought this in a store? You call this a what? Magnifying glass? Yeah, magnifying glass. It is magnifying. You guys see how it's magnifying like that? Oh yeah, that's interesting. All right, so magnifying glass. All right, so, hey, I wonder if that's the results we're going to see here. Now, remember yesterday we had to define a focal point to say how curved is this? And depending on how tightly curved it is, that would magnify differently, wouldn't it? Okay. So let's lay down a focal point. Now, because it's a lens, we'll actually lay down two focal points, one on each side. So let's go. Right. How about I'm gonna do about 6 centimeters out. Let's do 6 centimeters that way and 6 centimeters that way. Okay. So here's focal point, focal point. Okay. Okay. You're just don't have to be exactly the same length as mine, but as long as they're the same length as each other, same distance on the left as on the right. Okay. Now let's put an object somewhere between the focal point and the magnifying glass. Here, I'll go ahead and label this uh, magnifying glass. Okay. Put an object, say right here. Call this guy object. Okay, so there's an actual object there. Okay. Now, if the object is there and the lens is here, do you guys think some guy's eyeball might be over here? Okay, he's looking from this angle. Okay, looking from the right, looking left. That makes sense, right? That's how magnifying glass would work. That's what you guys just saw. Is that okay so far? Good. Yeah. All right. Now let's follow some rays. Now, here, just follow ray for ray with me, just like you did yesterday. Okay? But the rays for refraction are a little bit different than for reflection. So let's go from this first ray is going to be pretty similar. We'll just skirt the top of his head and we'll go parallel to the ground. Okay, so first ray across the top of his head, parallel to the ground, and take that all the way to that lens. Okay, is it? Now, when that light hits that glass right there, let's call this glass. What happens to the speed of the light again? The speed does what? Just slow down. Because it slows, it's going to refract, isn't it? It's going to, which is the fancy word for it's going to bend. Right? Take a guess. Which way do you think it's going to bend? Toward like up to the right or down to the right? Down to the right. Yeah, you're right. You're right. Right. It technically refracts twice, from the air to the glass and the glass back to the air. So if you want to make it real technical, you could do that too. Right? More on that later. Might round back around to that back. But the important thing is it's going to go through this focal point, just like that. Okay. Okay. So if you follow a single ray of light, like you shine a laser, it would refract down that way. Now, this person here, this person's eyeball, perceives that ray as having come from way up and to the left. As coming from like way back here. Okay, isn't that true? Okay. So this ray of light actually goes on this whole adventure, but this person's eyeball says, "Oh, it looks like that ray came from back this way." Isn't that true? Okay. Okay. Now, we need one more line to this whole deal. Okay, now this next one's definitely different than what we did for mirrors. Also, the fact the light crosses through it all, right? That didn't happen with mirrors, but it definitely happens with lenses. Okay. Let's go to the top of his head. So everybody at the top of his head. Okay. Now, any light that goes through the center of this lens pretty much just goes in a straight line. So we're gonna have it do that. Okay, the center of the lens. So do a straight shot right through the center. I'm gonna pause this video and grab this phone call right here. Okay. All right, and we're back recording. Okay. Did you guys? Maybe you guys have figured out where's the image going to show up? Do you guys see?
Parallel?
If you know how to interpret this, you guys remember yesterday? Here, we started with two lines crossing the top of his head, just the same here where they cross, right? And then we were bouncing lines all around. And there was another place where the lines would also converge, and that was where the image was showing up. Do you guys see the other place where the two lines converge? Right here. You guys see these two? Right here. There's the top of his head with the image. Let's put his feet on the ground, because if we did the whole thing for his feet would still show up on this ground line. Okay. There's your image. Hey, is that a magnifying glass? Oh yeah, I think it is. I think that's that right there, isn't it? That's the same thing. Yeah, that would be a magnifying glass. Okay. Okay, you guys good with that? Okay. Now, there's some other things we can do with this. So let's get the same lens all the way down. We're just going to do a bunch of converging lenses, so converging lens, converging lens. Okay. But what I'm curious to do is to position this object at different places, at different locations, maybe relative to this focal point. So this next one, maybe I'll put the focal points of the same place before, pretty close. Like right here, right here, right, focal point, focal point. Okay. What if the object is right on top of the focal point? Okay, what would happen there? Okay. Later on, we'll put this guy outside the focal point, and what's going to help us to also make the focal length a little shorter. Okay. So I'll do that. Okay, focal point, maybe a more tightly curved lens. You could think of that way, or you could say just proportionally, he's further out. Right? We're going to put him. I want to put this guy way out here. Okay, look at my pre-printed notes. Those are a pretty good place for me. Right. You guys good so far? Good so far. Okay. So what's going on with the second one? Well, let's see. We'll follow the same rules and maybe get a different outcome. We're going to find out. So let's go across the top of his head straight towards that lens, parallel to the ground, of course. Right. Okay, you guys do that. Okay. All right, then that's going to refract, of course, through this focal point. Like that. Refract, refract. Okay. Then go from the top of his head. And what was the last line we drew on the first one? Top of his head to where? The center of the lens. Remember that? That line pretty much just goes straight. Just straight here. Okay. So same story here. Just go straight through the center of the lens. Okay. And as long as your focal points are in fact equidistant from the center, which they should be, like mine's 6 centimeters here and 6 centimeters here. Right. Guys, these two lines are what? Parallel. Oh, hey, could this be a projector? Okay. Like maybe that one for my ceiling, right? Has some image back here. There's a lens. I bet if I look at that lens, it looks like a converging lens up there as I'm looking at it. Right? Yeah, you could project an image pretty good distance out, couldn't you? Yeah. Yeah, you guys see that? Okay. Or if you go the other way, later on, I'll show you guys what telescopes look like. Right? Could you maybe take some light like from the universe and converge it? Okay. And how about this though? What if the object is outside the focal length? Here, let's do the science version of this first. Here, see if I can. I forget if this works or not. Okay. But what if let's see, what would happen? No, it's not gonna work like the okay, take it, guys. This isn't gonna work on the camera. Sorry about that. But what I can do is I can turn like this and I can face all you guys. Okay, because from me to you, is it true if I hold this pretty far from myself, then my eye would be outside the focal point, and you guys, relative to me, would definitely be outside the focal length too, right? Okay. So tell me what you see. What do you see? Upside down. Do I look upside down to you? You guys look upside down to me. So you guys just told me that when I pan this around the room, we looked upside down compared to each other. Okay? This guy's outside the focal length. I wonder if the image is going to be inverted upside down. Do you guys think? Inverted image? Let's find out. Is the image going to be inverted? Because that's what the science was showing. We just tried it. Okay? So same set of rules. We'll follow one line across the top of his head parallel to the ground. Okay. And that's going to refract through this focal point. Refract through this focal point, basically. About like that. And what's the last line from where to where? Yes, head through the middle of the lens. Zip. Now, where do those lines also cross? How about right here? And his feet are on the ground. Oh yeah, that is in fact an inverted image. Inverted image. That's it right there. All right. You guys got all those lenses on your paper? You guys got all those? All right, so you guys get all those. All right, so next, flip the paper over And we're gonna do one with the diverging lens, and we only need to do one of these because where'd my ruler go? Okay. Once you do one, then they all kind of look the same. Okay, so let's label this one diverging lens. Okay. Just put a line through the middle of the paper, horizontal, like a ground line. Okay. Okay. Well, if converging looked like this, what do you think diverging is going to look like? Yeah, instead of fat in the middle and skinny at the ends, it's going to be opposite way. It's going to be skinny in the middle and fat at the ends, like this, like this. All right. Yeah. And if you have eyeglasses, depending on if you're farsighted or nearsighted, I always forget which one it is. I don't have this ready, so sorry about that. But depending on if you're farsighted or nearsighted, you need either lenses that are like thick in the middle, like these last three that we did, or thin in the middle, which would be like this diverging lens that we're about to do. Okay. So let's lay down a focal point also. So let's go here, whatever distance to the left side, put the same distance to the right side. Okay, so get a focal point, focal point. Okay, guys got that. Okay, and then let's put an object, say out here. Okay, again, wherever you put the object, get kind of the same result for all these. So it's sort of repetitive, but if you're curious, you can try a bunch of these. Okay, so there's my object. Okay, let's say here's this person's eyeball over here, watching this whole thing. Okay, so what does this person see? Okay, if you look through a diverging lens, what does it look like? Okay. All right, so let's get some rays going. So get a ray going across the top of this object's head, parallel to the ground. Okay. Now this time, when this light goes from the air to the glass, does it refract up to the right or down to the right? Up to the right. Up to the right. I mean, it's diverging, right? And I should draw this a little bigger. That's okay. You get the idea. Okay. Okay. And it's going to come out the other side at what angle? So that your ruler is aligned with what? This focal point. Yeah, this focal point. Okay. So if you want to, you could go, actually go ahead and do that. Go dash, 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 dash backward. Okay. The idea being this observer over here, like this eyeball, right, sees this light emerge this way, says, okay, there's a ray light headed that way. Okay. Therefore, thinks the ray light came back from that direction, which is going to tell something about what the image actually looks like. All right. Uh, what do you think is the next line I'm going to draw with you guys? Yeah, yeah. From top of his head through the center of the lens. Great. And just like the converging, this will pretty much go straight. So we'll just draw that as a straight line. All right. Now, where do you think the image is going to show up?
Below it.
Where the lines cross?
Yeah.
Right here? Right here? See where they cross? Yeah, there's your image. Okay. Again, no matter where I situate the object, the image always just looks smaller. So right, this observer here, looking through this diverging lens, should always see a smaller image emerge. Okay. All right, you guys go with those lenses? All right, so all right, I got some more poster examples for you guys and some video examples. And ooh, yeah, we're making pretty good on time. And then, okay, can you guys just turn this into the gray shade before you leave class? Okay, turn to the gray shade. Right, everybody's got all these images. All right, yeah, and I'll of course give you guys points for doing that. Okay, all right, so here's a recap. Here's the converging lenses we did. Okay, and here's the diverging lenses. Okay, so you guys get on the lenses, converging, diverging. I got those. Okay. All right, next thing. Now you can take both of these effects and create. You can explain rainbow physics. Okay. So, guys, when do you normally see a rainbow? When there's a lot of what in the air?
Water.
Yeah, water moisture, maybe like after a rainstorm. Yeah, a lot of humidity. Okay. Right, so you need all these water droplets. Okay. And guys, when you see a rainbow, have you ever noticed where is the sun positioned relative to you in the rainbow? Yeah, but which direction? Like if you're here, you guys see this person's eyeball? It says, "Oh, hey, there's a rainbow to the right." The sun is to the left, behind you, behind you. Guys, notice the sun is always behind you. The source of light that's ultimately causing the rainbow is always behind you, always behind you. Yeah, notice that next time you see a rainbow. Okay. Okay, so here comes white light, which is actually composed of all the colors of the rainbow. I haven't talked about colors very much with you guys, but maybe after spring break. Okay, after spring break, we'll talk about color. Okay. Uh, Actually, Isaac Newton figured this out. That's another activity I want to do with you guys. I'll prove to you guys. You can take all the colors and mix them together and create white light. Okay? Or you can refract the colors in. It turns out that every wavelength of light actually refracts a little bit differently. So the red doesn't refract as much as the blue does. Right? And the color spectrum, what our eyes can detect, that's the range. It goes from red has the long wavelength, and like blue or violet has the short wavelength. Okay? And then everything else in the middle. Right. So it refracts at a little bit different angle. Right. Now, if you follow, say, like a red ray, which refracts the least, right, and notice that there's actually two refractions. There's a refraction going from the air to this water droplet. This is a water droplet, right? And then there's some reflection off the bat. And there's refraction from the water back to the air. And this whole process, these colors are spreading out a little bit. It's subtle, right? So my drawing is exaggerating it a little bit. So it's a subtle effect. But here comes a ray of red light to this person's eyeball. Okay? And that will always happen at a 42-degree angle, right? If you like do all the math on it. Okay? Right. Then what about the violet light? Well, the violet light refracts a lot more. You guys see a lot more refraction and then reflection and then a lot more refraction. Okay? And actually need at least a second drop of water. So I have another drop of water to follow the violet light that goes bounce, 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 and goes this way. Okay? And it always comes in at a 40-degree angle. Right? If you see a full rainbow, of course, you need lots and lots of little water droplets, but you need at least two to be able to explain this properly. Okay? Okay, so, and then all these other colors are going to be somewhere in between those. Okay, and that's where you see the colors spread out and you see this rainbow. Right? So it's always going to be a circular shape. Actually, if you see a rainbow like this, you're really only seeing the top half of a complete circle. So you're seeing a semicircle. Right? But what if you're up in a plane in the sky and you're looking straight down and the sun's like 12 o'clock noon, like that behind you still, right? Right? Do you think you'd see like a circular shape, like a circular rainbow? Yeah, so like that. Right. And if you look close too, this is the main rainbow. There's actually always a double rainbow, and if it's a really strong effect, you can very weakly see a double rainbow. But all the colors were reversed, and well, I don't have that one up here, but yeah, too. Right. I think I showed this one to you guys the other day, didn't I? Because this actually happened kind of recently. Right. Yeah. So why does the moon turn red during a total lunar eclipse? Right. You're actually seeing all of Earth's sunrises and sunsets refracted onto the moon at the same time. So that's a refraction example. Okay. I got some bonus here. You guys ever notice if you look at butterflies' wings, they have like bright color, like shiny color. Same thing with like birds. Okay, and this color is actually not because of a pigment. Like this is not blue pigment. If you took the butterfly, let's say it was a dead butterfly, and you ground up its wings like with a mortar and pestle, it would no longer be blue. Okay? This blue is not because of any blue pigment. It's blue because of a nanostructure. So if you zoom down with a microscope and you see the nanostructure of its wings, looks like this. Okay? So it's actually this light hitting and bouncing off in a funny way, creating these interference patterns, right, which creates this really vibrant, shiny blue color. Okay? There's a different kind of iridescence that involves thin films. So if you see a water bubble, or like a soap bubble, I should say, a soap bubble, right, it has all these like sparkly colors on it. Okay? It has to do with this thin film and this light refracting, then reflecting, and refracting again. So thin films, and you also get that interference. Okay? So it creates all those colors. Okay? But right, let's look at a couple of telescopes. So let's start with this Keplerian telescope on the right. This is the design that Kepler used. Okay? Guys, what kind of lens is that? Is that diverging or converging?
Diverging.
Yeah, that's your converging lens there. Okay, and another converging lens here. Okay, now let's say that there's somebody's trying to see in the distance, have a galaxy, just for example. Okay, it's way off in the distance. Okay, now if you follow these rays of light, they're coming in parallel from like way, way, way far away. Okay, then they'll hit this converging lens and they'll hence converge. Okay, and then maybe there's a focal point right here, and it could line up with the focal point of this one. Right, and then so these lines continue. Notice they crisscross; they go the opposite way, and then enter this guy's eye. Now, do you guys see that what came in from the left is now on the right? What came in from the right is now on the left? Is that okay? So this person said, okay, it looks like this ray came from this way, this from this way. So if you extrapolate backwards, the image this person sees could show up a lot bigger. That's what a telescope does. But notice it's also inverted. Guess how it's inverted? Yeah, it's backwards. Right, right was left and left was right. Okay. Now, if you want to have a refracting telescope that does not invert the image, then you want the Galilean model. Right, so this is what Galileo used. Yeah, converging lens here. Oh wait, what is this, guys? That's not a converging lens. That's a diverging lens. You guys see diverging, right? Right. So now let's follow ray light. So the left side comes in, left, stay, and then um, it will transfer to the right. Right. But this guy says it looks like it came from way back here on the left. Right. So ultimately it shows up left matches the left. Right. Same thing on the right. It bounces over here, looks came from back here. Right. Right. And so you get an image that's not inverted, like that. Right. Now to go back to the rainbow, because there's something I gotta talk about here too. Right. Remember how every time there's a refraction, remember every wavelength the light refracts a little bit differently. Right. The red doesn't refract as much as the violet does, and then everything color in the middle is a little bit different. Right. So the colors actually spread out. That's called chromatic aberration. So for a couple hundred years at least, people were using these type telescopes to either uh, like on merchant ships or to look at the sky and do astronomy. Okay? But there was always a little bit of chromatic aberration. So if you're looking at, say, Jupiter, it looks like the colors are a little bit spread out, which is not ideal. Okay? So there's actually a different design you can create that gets around that, or at least most of the refraction. Okay? Because if you don't want there to be refraction, instead of using a lens, you can use a what? What's another curved object you can use that does not cause refraction? A mirror. Yeah. Right. Guess who was the first person in history to think of that? Close. Isaac Newton. Isaac Newton. You guys are all being little Newtons today. You guys figured that out. You use a mirror. It's called a reflecting telescope. All modern telescopes, or like serious telescopes that say NASA would use, like the Hubble telescope and the James Webb, right? There's some version of this. Okay? Instead of a lens here, they have a mirror. Okay? Right. So here's the object way off in the distance. You follow these rays light. Right? Okay, bounce. We've got a concave mirror here, right? And then maybe bounce off this mirror. Right? Now there might be a lens involved in the process, right? But this will get rid of most of that chromatic aberration, so you get a much sharper image. Yeah, there you go. And you can. Ooh, here's a Hubble Deep Field. So this has a fun story behind it. This was originally, I think, back in the 1990s when the Hubble was first in, or maybe it was 2000, I don't know, sometime 20, 30 years ago. Okay. Astronomers, of course, want to capture all different images with this telescope, the most powerful telescope at the time. And one team had this idea, hey, let's pick a random blank part of the sky, night sky. The size of the night sky we're talking about is like if you took a grain of sand and you hold it up at arm's length next to the night sky, how much sky would that cover? Like is an angular size? It'd be tiny, 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 right? Okay. So they said, let's aim at that. Now, if you know about photography, okay. Now I know modern day cameras, they have all this like rigged up automatically, but suppose you use a traditional shutter camera from a few decades ago. Okay. Because if it's bright outside, do you want the shutter time to be a long time or to be really short? If it's really bright, 12 o'clock noon, yeah, real short. Okay. So you're trying to capture a sports game, just short time, right? But if it's night, do you want a long exposure time? Long exposure? So to capture this image, they had to point the telescope. I think it was like for 10 days or something, like 10 days. So, and this was a really risky experiment because if it could have just shown up as black, and then it's okay, great, we wasted 10 days. We could have been capturing other things, but no, this is what we returned. And every one of these dots here is a galaxy. I think it's like a couple of stars, but pretty much these are all individual galaxies that have like billions of stars in them. Yeah. So this is the edge of the observable universe. Now, there's almost certainly galaxies beyond these, but it's just because of universal expansion. Anything beyond this is traveling away faster than well, because of expansion of space, faster than the light can travel back to us. It's a weird concept. It has to do with how space expands, universal expansion. Right. So, all right. Everybody got their ray diagrams in the gray tray? I'm going to close down this recording and play you guys some demos here. All right.